Hello, my name's Thanom and I'm from UNSW. Today I'm working through some of the Math 1011 calculus questions from section 2.6 on implicit differentiation and related rates. So in this question we have a sphere that is expanding, and it's expanding so that its surface area is increasing at 0.02 centimeters squared per second. So we're given, let's say the surface area is A and time is t, we're given dA dt and it's increasing, so it's positive 0.02. The units are centimeters squared per second. So we're given dA dt. Now we're asked to calculate the rate of change of the radius. We wish to find a dr dt, and we also wish to find dv dt, the rate of change of the volume, when the radius is 5 centimeters. So when r actually equals 5. So this is the question. Now, if we're given the rate of change of the surface area and we wish to find the rate of change of the radius, it would be really good if we had an equation that linked the surface area with the radius, which we do. Okay, so we know that the surface area of a sphere is given by 4 pi r squared. That is always true. To have an equation that links dA dt with dr dt, we're going to implicitly differentiate this with respect to time. So let's write that in words. Implicitly differentiating with respect to time. So in other words, we're finding d dt of both sides here. Well, this is just dA dt on the left, and 4 pi is just a constant, so this is 4 times pi times r squared differentiated with respect to time. Well, that's 2r times dr dt. We have to use a chain rule there, because if our sphere is expanding, then the radius is changing as well, so r is really a function of time. R squared differentiates to 2r. We multiply by dr dt for the chain rule here. So dA dt is just 8 pi r here, or if we want dr dt, let's write that as the subject. Dr dt is 1 on 8 pi r times dA dt. Okay, so that's just making dr dt the subject. So we can answer the question. We can find dr dt when r is 5 and dA dt is 0.02. So when r is 5 and dA dt is 0.02, dr dt is just going to be 1 divided by 8 times pi times 5 times 0.02. Okay, so on our calculator, let's first of all just calculate 0.02 divided by 8 by 5. So this is 1 on 2000 pi, if we want to keep it exactly. But actually, let's just keep it exactly. That's centimeters per second. Okay, so that's dr dt. Now, we wish to find dv dt. Now we don't really have, just off the top of our head, an equation relating volume with area, surface area of a sphere, but we do have an equation that tells us the volume in terms of the radius of a sphere, and that is, the volume is 4/3 times pi r cubed. So we could find dv dt in terms of dr dt, and given we've got dr dt here, that will serve our purposes. So let's differentiate with respect to time again. We're going to find d dt of both sides here. 4/3 pi r cubed. So this is telling us dv dt is equal to, well, 4/3 pi, that's just a constant. R cubed differentiated with respect to time is 3r squared times dr dt. Okay, so simplifying that up, we're after dv dt, so I might leave it that as the subject. This is going to be 4 pi r squared times dr dt. And I know dr dt this is 1 on 8 pi r times dA dt. So 4 pi r squared times 1 on 8 pi r times dA dt. And we can simplify that further because 4 will cancel, pi will cancel, and an r will cancel. So that will be r over 2 times dA dt once we neaten it up. Okay, so now we can substitute r equals 5 and dA dt is 0.02. So when r equals 5 and dA dt is 0.02, we have that the volume is changing, dV dt is 5 divided by 2 times 0.02. So that's a 0.01 times a 5, so that's 0.05, and we're talking centimeters cubed per second there. Okay, so this is a related rates question. We had a sphere expanding. We were given some information about that, and we wished to find how fast the radius was changing and the volume was changing. So it relied on us knowing a formula for the surface area and differentiating with respect to time to find a relationship between dA dt and dr dt, and also to know a formula for volume with respect to the radius, so we could differentiate that with respect to time and use the rate dr dt that we had found previously.